You ever sit in a physics class and hear something that just sounds made up? Like the idea that the distance a car travels is somehow the same as the area of a shape on a graph? It sounds kind of like a weird party trick, right? But it's actually one of the most important ideas in all of physics. So today, let's break down exactly why this works.
Look, we all get the simple formula. Distance equals speed times time. It's easy. If your car is on cruise control at a steady 60 miles an hour for 1 hour, you've gone 60 miles. Done. But real life isn't like that, is it? You're speeding up for a green light, you're slowing down in traffic, your speed is all over the place. So which speed are you supposed to plug into that neat little formula? That's where it all gets a little messy.
And boom, there it is. This question from a Reddit user just hits the nail on the head. They totally get it for a flat line, a constant speed. But the second that line gets slanted, meaning the velocity is changing, the whole formula seems to fall apart. Which v do you even pick? It's a fantastic question, and it's the one we're going to answer.
And this isn't just some random homework problem. Getting this is actually the key to how physicists describe, well, pretty much everything that moves. We're talking from a baseball flying through the air all the way to a planet orbiting a star. It's a really, really big idea, and we're going to unpack it together.
Okay, first up, a common physics puzzle, the slanted line. Before we can really tackle that slanted line, we have to be absolutely sure we get why the flat line works. So let's start there, with the easy stuff. So, let's just imagine something moving at a totally constant speed. On our velocity time graph, that's just a simple, flat, horizontal line. And the distance it travels? Well, that's just its velocity multiplied by how long it was moving for.
And check this out. The formula for distance, velocity times time, is the exact same as the formula for the area of a rectangle, height times width. In this case, the height is the velocity and the width is the time. They're literally the same calculation. So for a constant speed, distance is the area. See? Simple. But that brings us right back to the original problem. With a slanted line, the velocity is different at every single moment. You can't just pick one v for the height of your shape because there is no single height. The whole simple formula just breaks.
So the solution starts with understanding a really crucial difference. There's your instantaneous velocity, that's what your speedometer says at any given split second, and then there's your average velocity, which is your total distance divided by your total time. That distinction, as one of the Reddit commenters pointed out, is everything. For our slanted line, what we're looking at is a constantly changing instantaneous velocity.
So now for section 2. The tiny rectangles trick. Okay, if one big rectangle doesn't work when the velocity is changing, what do we do? Well, the answer is this beautiful, kind of simple but super powerful idea. Instead of one big rectangle, we're going to use a whole bunch of tiny ones. Take a look at this graph. I mean, the velocity is changing like crazy here. There's no simple shape, no rectangle or triangle that's going to fit that. It seems impossible to figure out the area, right? But what if we just zoomed way in? What if we tried to just estimate the area by jamming a few rectangles under that curve? For each of these little slices of time, we can kind of pretend the velocity is constant. Now, it's not a perfect fit. You can see all those gaps and corners where we're over or underestimating, but if we add up the areas of these rectangles, we get a pretty decent guess of the total distance. And here's where the magic happens. What do you think happens when we make those rectangles thinner and thinner and thinner? As we slice time into tinier and tinier little pieces, our guess gets better and better. The errors get smaller and smaller, and our group of rectangles starts to look exactly like the curve itself. This is the whole key. This Redditor, Sharog, just explained it perfectly. If you can imagine slicing that area into an infinite number of impossibly thin rectangles, the sum of all their areas, well, it wouldn't be an approximation anymore, would it? It would be the exact area. And this amazing process, this idea of summing up an infinite number of teeny tiny little pieces to get a perfect, precise whole, it has a name. It's called integration. It's one of the cornerstones of calculus, and it's the tool that lets us find that total distance perfectly, no matter how wild the velocity gets. Now for our third and final section, slope and area, an inverse relationship. So it turns out, this whole tiny rectangles trick isn't just a clever solution to one problem. It's actually one half of a really beautiful, fundamental relationship in both math and physics. Think about it this way. If you have a graph of an object's position over time, how do you figure out its velocity? You find the slope, right? The steepness of that position graph tells you the instantaneous velocity. That process is called differentiation. It's all about finding a rate of change. Okay, now let's go backwards. If you have a graph of acceleration over time, how do you find the change in velocity? You find the area under the line. It's the exact same idea we just learned. You're summing up all those little bits of acceleration over time to get the total change in velocity.
And that right there reveals this incredibly deep connection. Finding the slope, differentiation, and finding the area, integration, are inverse operations. They're two sides of the exact same coin. One builds things up, the other breaks them down. Going from position to velocity is differentiation. Going from velocity back to position is integration. They perfectly undo each other. It's beautiful.
So let's just put it all together. We started with a simple problem, a simple rectangle for constant velocity. We saw how that just doesn't work when things get complicated. But then we found this amazing solution, slicing the problem up into infinite tiny rectangles. A process we learned is called integration. And finally, we saw that this whole area idea is the perfect opposite of finding the slope, revealing this amazing symmetry at the very heart of how we describe motion. So you see, the area under the curve isn't just some random rule you have to memorize for a test. It's like a window into how the universe is actually built. It shows us that for every action, like finding a rate of change, there's this equal and opposite reaction, like summing all that change back up. It kind of makes you wonder, doesn't it? What other profound hidden relationships like this are out there, just waiting for us to draw the right graph?